Hello everyone, let's go ahead and begin by taking a look at integration by U-substitution. Now I have up here two integrals, this one and that one there. If you had a choice, which one would you do? Would you like to do this one or would you like to do this one? And I'm hoping that everybody would obviously say, this one, I want to do this one. And the reason why, of course, is because this one is so much simpler to do. And this one almost looks like it's impossible. Now, if we wanted to go ahead and do this, we'd have to use the binomial expansion, then distribute the 2x minus 1, and then after that do the sum and difference as well as the scalar multiple over. Oh my goodness, this one gets so difficult. But in reality, what happens is that this is actually the same thing as that. And the way that we can do that is by what's called a U-substitution. Now, when do you use the U-substitution? The U-substitution is when you actually take a look at the differentiation of a composite function. And so in other words, a chain rule. So this is the result of a chain rule. So what integration by U-substitution actually does, it undoes the chain rule. So if I take a look at this, notice that I still have a composite function and then I have this other part here. And what's important to realize is that the derivative of the composite part that's inside is actually going to be a part of the integral itself. So let's just go ahead and say that. Let's say that let u be equal to this part right over here, the x squared minus x. Now the reason why we wanted to go ahead and let u be equal to the x squared minus x is because if I take the derivative of u with respect to x, I come up with 2x minus 1, which is the derivative. Now it's important to notice that the 2x minus 1 and this 2x minus 1 is there. So the derivative of the inside of the composition of functions is actually a part of the integral. Now what happens then is I'm going to just multiply both sides by d of x. So d of u is going to be equal to 2x minus 1 d of x. Now, hopefully what everybody can realize at this particular point then is that this part right over here, which is of course equal to u, is that part there. And if I go ahead and take a look at the 2x minus 1 d of x, that part is right here. So notice that if I go ahead and change everything by using this u substitution, then basically what happens is I come up with this. Because I know that the x squared minus x is actually u, that's u to the fourth. And all of this part that's left over, the 2x minus 1 times by d of x, is actually the same thing as d of u. I've come up with my solution there. Now, I can actually now go ahead after doing the u substitution and just integrate with respect to u. So I just have to use the power rule here. So this is just going to be 1/5 u to the 5th plus c. Notice again, I always have to include the plus c, which is my constant of integration, and I'm done. Except for the fact that my original integral was in terms of x. How do I get this so that it's in terms of x? Well, it's right here. This is what u is. U is equal to x squared minus x. So this then becomes 1/5 x squared minus x to the 5th plus c. And there you go. You're done. So notice that what happens then is you start off with x, you look for a u substitution in here because you have a composite function and you're trying to undo the chain rule. And what you come out with is something that is completely in terms of u. You cannot have anything in terms of x. Everything has to be in terms of u. Then I anti-differentiate with respect to u, and then I resubstitute back into x. Okay, so hopefully that example was clear. Let's go ahead and take a look at another example here. Let's say that this is example 1. Let's go ahead and take a look at example 2. Example 2 says we have an integral of 1 minus x squared divided by x cubed minus 3x d of x. Okay, now notice in this case, of course, we have to try to look for the composition of functions. And in addition to that, we have to think, if we go ahead and let u be equal to something, will that derivative be in the integral itself? So let's go ahead and say let u be equal to, now I can't let it be 1 minus x squared because there's no derivative there. But if I was to let it be equal to x cubed minus 3x, watch what happens. d of u over d of x is now going to be equal to 3x squared minus 3. Okay, so now that doesn't look like anything that we have up there until you actually go ahead and change things a little bit so that I can actually get it like that. So I know that d of u is going to be equal to, let's factor out a 3. This is x squared minus 1 d of x. And now notice that the only thing that has to happen now is this just has to change. It has to be 1 minus x instead of 1 minus x squared. So this is the same thing as d of u is equal to negative 3 times it by 1 minus x squared d of x. And now I want to get this by itself, so I'll just divide everything by negative 3. So that's negative 1/3 d of u is equal to 1 minus x squared d of x. Okay, so let's go ahead and see if we can find all of our substitutions here. This right here is that. This part right over here is all of this. Okay, so now we can actually go ahead and change this so that it's in terms of u. So this then becomes the integral. This whole red part over here is negative 1/3 d of u divided by, and this whole part under here is just u. So I can use my scalar product rule and scalar product multiple rule, and I'll bring this up in front. So this is negative 1/3 times the integral of d of u over u. Okay, so what is that? That is the same thing as negative 1/3 times the natural log of the absolute value of u plus c. And then I just have to resubstitute the value of u in terms of x. So this is going to be negative 1/3 natural log of the absolute value of x to the third minus 3x plus c. Okay, and then you're done. All right, let's just take a look at one last example here. Just make sure that we can actually do these. This one's going to look a little bit more tricky, but it's basically the same technique. Here's number 3. It's the integral of 1 over x times it by natural log of x quantity squared d of x. Okay? So we have to think, if I go ahead and let u be equal to something, will that derivative actually be in there? And hopefully you can see that if we let u be equal to the natural log of x, then d of u over d of x is equal to 1 over x. Then d of u is equal to 1 over x d of x. Okay, so again, we have everything that we need again. So notice that the natural log of x is right here. And then notice that this 1 over x d of x, well, here's the 1 over x d of x, x squared. 1 over x d of x. So if I was to go ahead and change this into its u form, this is the same thing as the integral of, let's see here, we have 1 over u squared, and then that whole part is just d of u. Okay, so this is the same thing as the integral of u to the negative 2 d of u, and now I have to use the power rule. So that's going to be the same thing as 1 over negative 1 u to the negative 1 plus c, and then I just need to go ahead and resubstitute in the value of x. So this is just going to be the same thing as negative 1 times it by 1 over the natural log of x plus c. So we can just write this as negative 1 over the natural log of x plus c. Okay, and then you're done. Okay, so that's basically what you have now. You have, by using the U-substitution, you can actually undo the differentiation when the chain rule was applied. Okay, so there you go. Hopefully you can actually do these by just practicing and making sure that you can see if you let the u be equal to a particular function, a particular part of the composition, that the derivative will actually be in the integral itself. Okay, so give it your best shot. Let's see how you do. See you later. Bye.